like it has because anyway.
Okay.
And it's the most important thing is just the
Okay. Yeah, it's completely step behind. But I still don't think
no.
Okay.
So that's that.
Okay.
Okay. So it seems someone else is also bottom coming here minus like half.
2/3 of it.
Missing.
Yes, but we will not divergent positions.
Like
After you what's on now.
before I start, the question is that do I keep just 1 hour or how many can stay here for 2 hours? So not everyone can stay. Okay. So I'll then have 1 hour, and then those who want can stay to talk and discuss. But I'll otherwise, like the most important things I'll continue then Thursday. So it takes a little bit time to those projectors come up. So I'll start on the chapter 6. I have time to say a little bit about also chapter 7, but it's also that there's extra material for chapter 7. Which was mentioned in the reading instructions, and there was, so in January I gave one model selection tutorial which was videoed. Unfortunately, that video is not yet online. I hope that it will be online before next week. So you can also then check that one. Um, so chapter 6 and 7 are paired in that way that they have some connections. It's overall about the connection is model checking, and so that in chapter 6 there's already also mentioned cross validation, and chapter 7 has more on cross validation. And then on the other hand, especially these the features of the diagnostics of Pareto-smoothed concordance sampling has turned out to be very useful model checking tool too. And so I show you some demos on this model checking. So now you don't have assignments which would require posterior predictive checking, but then that requires in your project work, unless you will get exception for because of the some of you asked for a topic where this model checking as the posterior predictive checking can be more difficult, but most of you hopefully have a project where you can test it. And also these demos, I also have many examples. Overall, when we have results from our model, we should of course look at it. Do they make sense? If we are testing model for hazardous chemical, and we would get a result that higher dose would reduce the probability of death, then we should of course check our model, even if we did not include that information in the first part. And it's quite common that we first want to make quickly some model, and then if then that model seems to give strange results, we can then refine. The reason for what is that sometimes the prior information we did not use for building a model was such that presenting that in mathematical form might be sometimes difficult, need more thinking, and then we first avoid thinking, and then only if the results are strange, then we do more thinking and for this additional information in mathematical form. We can of course the kind of how science works is that we make some hypothesis, and only that kind of science can be validated, where we can make some predictions for the future and then make new observations in the future, which confirm these results. I think a good example is this: the Einstein's relative theory and predictions for what happens when light passes a heavy object. You can make a prediction that an apparent direction of stars should shift a little bit when they are really close to the sun, and then even if the actual measurements were noisy, it was strong evidence because it was something that Einstein did not first have measurements, then fitted the model E equals to mc to alpha, and then optimized what's the value for alpha, but had a prediction, and then even the weaker first measurements were convincing because of And then, of course, there are the then fields where it's really difficult to make replications. Like in archaeology, it's difficult to repeat what these people did really do. How did they really build pyramids? It's of course possible to make theories that, okay, if you would have these kind of tools, it would be possible to build this. But it's still difficult to repeat that whole process. But then, even if we don't have that additional information, or if we don't want to wait for getting new data, we can do this internal validation using the model already. Data. This is the demo 6.1, and this is so that we use the model to write speed data and then replicate so that we can generate from the posterior predictive distribution draws, new data sets, generating as many draws as was in the original data set. And then one of these histograms is the original data and others are replicated data sets. If you can now easily find the original data and you can see how it differs from replicates, then it means that our model was somehow not able to capture. Can you see where the original data is? Number 6. Yes, it took a moment to figure out whether the numbers were top or bottom of it. Yes. And so this is the basics of this posterior predictive checking, that after you fit the model, generate data from it, and compare it to the original. It is possible to do it even like this, looking at the histograms, but then if your model is regression model, it's more difficult to look at how your distribution looks like for different coverage values.
In these plots, all the plots have about the same mean, but then the true plot, the original data has lower variance than all the other plots. But isn't that naturally if you're trying to generate a whole lot of other?
If you use the word,
get a higher
if you use the word variance, they have the same variance also.
They do? Oh, right.
Yeah. So it's because.
Oh yeah. So yeah, you got one on there. Yeah. Makes sense.
Yeah.
Makes sense.
But then, even if they have same variance, we can see that there's a group of observations which are grouped narrower, and then a couple of outliers. It could be a description. And in that way, then now we can see that, okay, there's one replicated data, the one group is wider, but we rarely see the small values. And since it's even so for this histogram, it was now difficult to see really where the problem is. Because the regression models, it's even more difficult because you might have a case where your model fits well for some of the covariate values, but not the others. So we can, instead of then repeating few of these, we can repeat this same generation process, for example, 1,000 times. And then for each 1,000 replication, for example, here, because this one is kind of strange, we could check that how small values we see from the replicated data. And we use the test statistic, which is the minimum value. And here's the red line shows the observed smallest value. And the histogram shows smallest value from 1,000 replications using this model fitted to the data. And we can see that in 1,000 simulations, the smallest value was here, which is quite far away from the smallest value. So we can say that, okay, it's not capturing, can't explain these small values in the data. Of course, now we could say that these two observations, really small observations, maybe they were outliers, maybe it was removed from the data, maybe they were erroneously coded. Sometimes that's fine. For example, if we, I was just making a case study. Example data is predicting body fat percentage, and then that data has a person who is just 30 inches tall. And then it's likely that instead of trying to make a model which would explain that sometimes someone makes a mistake writing these numbers up, the measurements, just remove that kind of wrongly coded, because it's not always necessary that we try to model the whole data collection process. We would model also what's the probability that someone makes error when making a measurement and then typing these numbers up. Of course, there can be cases also where we want to do that also to model these data collection errors, especially if there would be more of these kind of errors. It's possible then that if we remove everything which looks suspicious, we remove too much data, and then again making a model which can use, for example, from each person, if we have different measurements, we don't throw that person away if one of the measurements is really strange. We can still make a model which is robust for these errors. We could model also this data collection process. And now, since we can do this, the replication, and we can even then compute this posterior predictive p-value, which then says that what was the probability over these replications that this is more extreme than these replications. Now the choice of this test statistic is important. So since we are using the same data first to fit the model, and then we generate from the model, and then we use the same data to make this comparison. That test statistic should be orthogonal to this model. And this minimum was good because our model had only mean and variance. And so it didn't have skewness or kurtosis properties, which would explain longer tail. And this shows that, this demo shows what happens if we use variance as test statistic. So now, since our model had the variance property, the replicated data has the same variance as the true data. And of course, there's a variation now because we draw finite number of these, the same size of the data set, and then when we repeat, recompute the variance for these replicated data sets. This means also that when we get more and more complex model, so that there's more and more parameters. It's more and more difficult to choose good test statistic for this posture predictive checking. So that in extreme, if we have non-parametric model which has as many parameters as this data, it's quite likely that we can explain all these kind of features, and then it's really difficult to come up with test statistics which would be any more revealing the problems. However, we can then use cross-validation to avoid alleviate this problem. Before going to this cross-validation part, there's another example was we have sequence of observations. So this was also in the book. We once what the question is that can we use binomial model so that is there any time dependency in this, or can we assume interchangeability for those and then use binomial? And then there was a test statistic that count the number of switches from 0 to 1 and from 1 to 0, and then there's a code and then it computes. We can see that then in the, and since the binomial model doesn't model the number of switches, this is a good test statistic. You can see the red line and the distribution group replicates. And now we might then suspect that maybe there is such time dependency in that sequence of observations that just the binomial model is not sufficient. There's I'll show you more examples. So if you are using R, there's a Bayes plot package which helps when using Stan to make these posture predictive checking plots. I'll show you a couple of examples. So I will briefly mention now the cross-validation already now, but then I'll talk more about cross-validation later. So now with the posture predictive checking, we are using the data twice. And only if the test statistic is well chosen, we can see these problems. And it's also more likely that we see these problems, especially when we have small number of parameters more data. The cross-validation divides the data in two parts so that we use some part of the data to fit the model and other parts to test the model. And we can use it also then in this predictive checking. And here with this marginal posture predictive checking is such that we are looking with cumulative densities. A light speed example, observation here and here, and then you have observation here. If you take the model here, it was then mean here, and the Gaussian distribution like this. And then we can compute cumulative density function so that how much mass is here, so it's close to 0, still quite close to 0, and then we would get 0.25, 0.8. So we would get value from each observation. And now, if those observations would be coming up from our model, then the distribution of these cumulative density function values should be uniform. So here it's called marginal posterior predictive checking, and then it's also sometimes here's also term pit value, which is the probability integral transform. And so the cumulative density function value is now then this probability integral and transformation referring that we transform each observation to then this probability integral value. So now if you look at this so if you look at this light speed example, we can see that it's not uniform. We can see here this one is this observation, next one is this one, and then there's the bunch of these observations here, and we can see that these are clustered too closely, which is because our model was made too wide because of these outliers. So this is wider than the true data distribution. And so these are clustered now closer to 0.1. So we can see also from here that there's something wrong. Now we remove the two outliers. So if we assume that it was only a problem with these, let's see what happens. We get much better results with those outliers. So without those outliers, it's likely that our model is quite good. And now it's, of course, randomness then that how we say that when this is uniform, because even if you draw from a uniform distribution, there's always random variation and it's not exactly equal histogram. But now we can also then, oh, I thought that there would be the also the cross-validation version, but it wasn't here. But at least you now know the pits, and I have the cross-validation version coming later in the examples. Questions so far? Oh. So these are the positive predictive p-value. So it is also possible that this test statistic would also depend on theta. I don't remember many examples like that, so it's usually, I don't now remember even a single example where it could be used, but it's possible. So usually these test statistics depend only on y, and then it's either the replicated y or the observed y. And then this is just showing that how we here look at it's the posterior predictive distribution, and this is the indicator function. How many times we observed the statistic for the replicated data, which was larger than for your circuit. So this is from, so it's preprint is in archive, and it's to be up there in Journal of Royal Statistical Society, paper on overall visualization in Bayesian workflow, looking at the different parts of the workflow, but also it has some of these checking statistics. So the example used in that paper is this, that how much there are these air pollution and specifically particles in size less than 2.5 microns. This size is special because now it's small enough that it can get to the lungs and to the lung pores, and then seems to that where you have a lot of this size particles, you will get a lot of different diseases. This is risky higher than in a thinner. In overall, then to estimate this, that how globally people are exposed to this kind of air pollution, it's possible to estimate the amount of this PM 2.5 also from satellite images, but then it's not exact measurement, and in addition, then there are measurements at ground level, and now then there are at different locations there are more or less of these measurements, and then it would be nice to be able to use the satellite measurements, then predict also for those places where there are no ground level measurements. So there's now in this data almost 3,000 locations ground monitors, and then there's the high resolution satellite data, aerosol optical depth, and this plot here. So it's the log value of the satellite estimate and the log value for the ground monitor value. And we can see that they correlate. It's also now that there's a reason to believe that in different kind of regions there might be variation in this correlation, and then that's why there's these colored dots for different regions. These are these WHO super regions in this book. And now there's the on the left-hand side, it's these WHO super regions colored in maps, and on the right-hand side is it's based on cluster analysis of the data. The bottom plots are just now exploratory analysis, so there's individual linear model fitted to these different cluster data. And we can see that in a way this model checking can start in that early phase, that even in a way that if we look at, okay, there's a linear model, is that reasonable choice? Maybe if we put different linear models, maybe we should have a hierarchical. So in that way, we have these kind of checking of our ideas how to think about the data going on all the time in different ways. There's also the chapter 6 discusses more about the posterior predictive checking, but there is also prior predictive checking. So that the question is how we should choose priors. And one way to check that whether we've chosen reasonable priors is also then to generate the prior predictive draws before conditioning on the data. The first plot shows then weight priors. And this was the so when in the mid 20th century there started to be these arguments between different schools of statistics, so and then eventually leading to these terms frequentist and Bayesians. At that time, then frequentists said that the Bayes is bad because the choice of prior is objective, and subjective is subjective, and then Bayesians wanted to be objective and proposed lots of ways to make really weight priors. Now, if you have improper prior, then you can't even get anything sensible out of predictive distribution. You need to have proper priors. Even then, it's been for a long time recommendation to use as vague priors as possible so that you would not be influencing your inference with priors. But then, in a way that the priors are non-separable part of the model. You can't have model without parameter space, and as soon as you have a parameter space, even the uniform prior states there's something. And in that sense, then the prior predictive checking is then sensible part of the already that you think that beforehand, is my models that kind of model that would produce something which looks like our data. Okay, let's see what happens with these priors we're using. With the weight priors, you can see observed log value is going from 1 to 5. With weight priors, the log value is from 200 to 800. So it means that there's kind of huge difference in even in the order of magnitude what we are saying with our priors about this. With weakly informative priors, our predictions are still wider than the truth, and that's one. But at least we are around the correct order of magnitude. And then weakly informative prior, the weak comes from that, okay, that if we make draws from that prior, we should not get predictive distribution, which would be, again, really concentrated, having a like smaller variance than the observed. That's also in the other way we could say that how we can check that we are not using too informative priors. So with too informative prior, our simulated data would have then narrow variance, and maybe it would be then also again still far away from the values we observe. But this looks nice. Magnitude is right, not far away from the observations. Here's posture predictive checking. So it is a regression model, but we can still just make the density estimate of all observed PM 2.5 values, and then we can generate these posture predictive distributions. And the model one is just one linear the model one slope and intercept for all the data. And models 2 and 3 are, so this is so that we have a different linear model for these WHO regions for then the clustered regions. And these are hierarchical models. So remember here, these were independent linear models, and it seems that we should have a hierarchical model to reduce the variance. There's some similarity in the slopes. So we can see that, yes, the model improved. There are some kind of the small changes here, and now it's also it's not so clear, easy to see from this that everything's fine. There's another one, posture predictive checking using the statistic. Okay, so back to this. So this is kind of same as I had the figure for having several histograms for the light speed data. Instead of histogram, when we use density estimate, then we can overlay several of these density estimates in the same figure. So we see also that the variation in the model. In this case, there's so much data compared to number of parameters that there's not much variation, and then the replicates are quite similar to each other. We can compute skewness of our predictive distribution and skewness of the data. We see for the model 1, this big difference in skewness. Model 2 and model 3, we see that the observed skewness is kind of reasonable compared to skewness of these posture predictive distributions. And it's also from the Bayes plot, we can also look at these test statistics for different groups. And again, the first model, the non-hierarchical model, good model, really bad. And this is now the median for groups, and we can see that sometimes the median was lower or higher. Here, much more reasonable results, although they are like for this group here. Of course, it's now that we start to have this kind of the problem of multiple testing, and it's possible that it was just by chance that this is here and this is here. So I talked about this PIT, probability integral transform, and here you can see that if these PIT values would be uniform, they should look like this. So this small bench here is because of the kernel density estimator we're using. Otherwise, these are uniform. And the black line is what are the PIT values for the model when we use the Leeuwenhoek performance. And you can see then that model 2 and 3 are performing better in that sense that they are closer to uniform, but they are still room to improve. So in this paper, we didn't go beyond these model 2 and 3, and then there's the group from which we got the data. They did also more elaborate models for this. So that it's also then possible to take, for example, into account the elevation, which is reasonable that will affect the optical properties from the satellite. So, questions? No. Okay, then. So these slides are not yet in DTU inside the folder where they are the lecture slides, but these slides are anyway on the internet. So there's the repo here. I will upload these also to DTU inside. And so now, since I have only 20 minutes today, I will only start the beginning of the cross-validation and then I'll continue on Thursday. And also when I talk about cross-validation, I'll come back to details of the V1-out probability integral transformation statistics. But then, so there's the chapter 7. It also discusses then the overall model assessment and model selection. The chapter 6 was more about the kind of try to find something what is wrong in your model type of thing. But then, if we don't find any more kind of these problems in our model, we might be interested in then is just knowing how good it is making predictions, so that that model would be used to in hospital, so that when like there's someone getting stroke coming to hospital, and then they need to make a quickly decision that do they operate right away, or do they wait, for example, if it's during the night, do they call the doctor to come in and operate right away, or can they wait to the morning? And then we know that the outcomes would be then that, okay, operate later, who died, who didn't die, operate right away, who died, who didn't die. And we have then some expenses for this. And of course, remembering, this is not just that it's cheaper to operate later, there's also always also risk in any surgical operation. So that might be also a reason that do not operate because this person will survive anyway. And then before letting this model to make these decisions, it would be nice to know how good decisions it makes. Of course, we could just let it give decision suggestions, and then we would not make the decision based on what it says, but just record that if the doctor did this decision, what happened. But even before that, kind of the waiting what happens in the future, we can do this predictive model assessment. And we can use then cross-validation to do that, so that we use, and I would now assume that you have also cross-validation in some machine learning courses. So how many are familiar with cross-validation? Okay, not everyone. So have the data. In quantitative predictive testing, we used all the data. Now in cross-validation, the simplest one would be divide the data in half, use this to system model, predict what happens to the other part, and then check how well that really these predictions work. If we divide the data just in half, we have the problem that we are using only half for fitting the model. And so it is common that instead use bigger part, fit the model, small part to test, and then change. And instead of leaving this part out, leave this part out and use then this part and this part for model fitting. And then we can this way go several times using different part for fitting and different part for testing. We can also test that how good predictions we can make. And then I'll talk a little bit about these utility functions, cost functions also. But in a way that if we know now that our model is good for predicting who should be operated and who not, and then there's no need for model selection if we found this fit model and we put everything in there. So I have this model rich enough, capturing a lot of uncertainties. So assuming that anything we thought that this might be relevant for making this prediction, let's put it in the model. Or we don't know what this parameter value should be. Okay, let it be unknown parameter and have a prior for that. Making this kind of rich model, look at uncertainties. We did the model prediction. We didn't find anything with partial predictive checking or blue fit, and we saw that yes, it gives good predictions. No need for model selection. Interesting was that in NIPS 2003, people organized teacher selection competition, where especially when they announced this competition, they were saying that they would assume that there would be better predictions after feature selection. And Bradford Neal used Bayesian approach, used combination of some PCA just to do some dimensional reduction, but using still got all the features, PCA and Bayesian neural networks. And then he won this competition, so no need. And he had really elaborate competitions. And of course, when I say that we have this rich model and we are happy with it, we can still think that, okay, it's still just an approximation of the real world, so it's wrong. It can be useful for making predictions. And there are known unknowns, which are those which we put in the model, and the unknown unknowns, which we didn't come up that we should put in the model. So it is possible that we are making such predictions that suddenly there comes different type of patient in, and because there was some unknown, we can make wrong decision for some patients if we didn't know what to take a look. So I think that the model selection should be done only then if then some smaller model, or if we have used non-parametric models, what if some parametric model is practically as good? And only if we can then ignore some of these uncertainties we had in this rich model. And the reason why we might want to do this is that we have reduced measurement cost in the future. So as soon as the patient comes in, what are the measurements we take to decide whether they need to be operated? In this case, the measurement cost might be not euros or crowns, but it could be also how much time it takes to make different measurements. It's also simpler to explain. If the rich model has 100 different things we can measure from the patient, but if we can make as good predictions with just 5, it's much easier to explain to doctors that, okay, look, now we have this model which is using these 5 things, and these 5 things mostly affect this way to increase or decrease the probability that need to be operated quickly. So now for that is the it's quite rare that you would be in a such situation that you would really be having the model in like in a hospital. More likely, okay, of course, if you are working on that they are advertise web advertisements, how many clicks you will get. It's quite likely that you are estimating the predicted performance of the models. There's a lot of the financial situations where you would be doing this. In a way, we can also see these autonomous robots and cars and so on are doing it. Actually, these kind of reinforcement learning things are doing this decision analysis all the time. And we have the decision analysis doctor still in the future. So I'll then talk more about the different decisions, and now this is more about just how to do these computations, how we can estimate the predicted performance for a model. So here in this question, we have the predictive distribution. Now the capital D is the data which has the x's and y's. And then we have some specific model and K. And this y tilde is something we haven't observed yet. So we might think that, okay, this is now the, that there could be then also x tilde. So the mutation comes in. What do we predict? And then again, now the floppy notation. This can be now the predictive distribution for y tilde. But then sometimes this also means that now we actually evaluate the density given some future observation y. So that it could be and then if this would be just the probability, patient died, did not die, we could have then also then. So this would be the distribution, and then we would have also probabilities that we actually observe, would observe in the future, did not die or did die. Now, of course, in this kind of the patient died, did not die, you could then look at the more of the specific utilities, but it's information theoretically justified use this log score if we want to know just overall how good our predictive distribution, how good this model is to make the predictive distribution. And so we want them to evaluate, like here, then it would be the log probability for not dying and log probability for dying. But since we don't know beforehand whether someone will die or not, we can compute expected log density or log probability. And in this case, then there's the PTY, which is something that we don't really know, which is the kind of true future distribution, but which is not in real life available for us. But still, if we would be able to see this, if we would know this, then we can integrate over uncertainty about the future distribution. So we would get, so let's say in this case, probability of not dying 0.7, probability of dying 0.3, and then the log score would be this one plus this one. Now, since we don't know the PT, we have to approximate the PT somehow. Bernardo Smith listed these M open, M closed, and M completed. In M open, we assume that none of these models we are analyzing is not a true model. In M closed, we assume that one of the models we are comparing is the true model. And then in M completed, it's the kind of one of the models is our reference model, which we assume that is close enough to true model. So now we can, the M open is the one case where we don't want to make any assumptions about this when we are doing the predictive testing of the model. And we can avoid it. So we reuse the observed data as pseudo Monte Carlo samples from the distribution of future data. So if the future data has the same distribution as the old data, we can use the old data as a pseudo draws from the future distribution. And now, in order that we are not using the data twice, we just then have to replace these log probability densities here, or log probabilities version where, so we replace the y tilde with yi, and then we remove the yi from the data. Now it's also then, the slides are slightly floated, that sometimes I have the PT just y tilde. I should have then PT x tilde, y tilde there. Because in the next page, when I do, so the leave one out approximation for that integral, then I have the y's and x's. And it's also quite common that we don't make the model for the x's at all. So this will also now form as an approximation of the x's distribution in the future. And then we just take the empirical average. So then this is the kind of theoretically justified, and this is what we try to estimate. And it can be shown that then it's almost unbiased estimate of this. And then we can use other utilities or cost functions here instead of this, and then again replace them also here. So it's now 4 questions. And then, so Thursday, I will continue with the computation, how we can do the computation efficiently. So if you look at this one, this is the requires computation of the posterior distribution n times, where each time leaving just one observation away. So next time I will then explain how we can use importance sampling and that's what Stan does, so that it's enough that we run the sampling using all the data, and then we can use importance sampling to give us approximation for the leave one out these computations. And then I will also talk about how that approximation actually then turns out to be useful for also model diagnostic. The importance sampling doesn't always work, and so it is very common then to overall in statistics and machine learning to also the k-fold cross-validation. So we divide the data, for example, in 10 parts and leave just always one part away. Usually, if we need to redo the full computation 10 times, that's not infeasible. Mentioned that it's robust because so that it's more robust than the importance sampling. But the importance sampling is good in that way that we have a diagnostic which also tells when it fails, so that you can always run first the importance sampling version, and then only if you need k-fold cross-validation. Although also next time I will tell that there are that kind of predictive cases where the k-fold is usefully up for hierarchical. Your assignment is then for this. So this one, so there's a hierarchical model, factory data, and then you're using the parent smoothed importance sampling level out, so the key Thursday. And then you compare hierarchical model and food model in this factory data case.
Next week we have to present our project.
So you need to present what's your project idea.
Okay,
So the project doesn't need to be finished yet. Yes.
But how long time should we talk? Should we have slides ready or?
So it would be useful to have slides, just few slides showing that what's your data, what kind of model you are going to use, that's the plan. So depending on, of course, in a way that what's your data, you might have many pictures and then you may have many slides, but overall, I would say maximum 5 minutes per group.
Okay. And then 2 weeks later, we have to hand in a report.
So there was more. I have to check again with Lula that what was the deadline, but I think they were more than 2 weeks.
Okay, but we have to make a report, and after handing in the report, we have to go through all exams as well.
Yeah, so there will be then that's the session where you all come, and so that you will present the results of your project to other students too.
Okay, so it's not an exam where everybody will be there and you
Yes.
show your results. Okay.
Yes, and it is possible then that I would be also present here, or I'll be then following through video. But since there's too many times audio problems with video, and then it's really annoying and difficult to give feedback. So I would like to give feedback, so I'll check if I'm able to come.
Okay. And when will we get this date? Time? We don't know yet.
This week.
Okay.
Yeah, I can decide it this week. Yes.
And what happens if we can't come?
What
happens if we are not able to come?
Yeah. So if that date is not, so of course we try to choose a date which suits as many as possible, and so we can discuss this on Thursday. But if we can't get a date which suits everyone, then you need to present separately to Google during agreed time. I think there was like last year maybe 1 or 2 groups who did then present only to Google. So usually we've had, or usually what we did. Every year we have had great student presentations, lots of discussion, and learning more about how to think about this modeling and model checking. Yeah. And so if you have to go, then it's fine to go, but if someone who wants to stay, then they can stay for a moment. Yeah.
Basically, it's 100% features of 100%. Then you know, yeah, this is so it's you're either sensitive all the system changes. But the problem is this is the features that is like otherwise and all in the lab something like
So 64 is number of cases.
it's number of these cells which is yeah, but it is too much cells.
Again, 5 is
The number of ones. So it's in the cell, every cell is exposed, so I so which is the
okay, and then it is 200 or So that with straight line pattern here, so this here is fixed for my sixth coordination. Then I expose my
Hvad siger du? Ja, jeg har ikke gjort noget. Jeg tror for mig.
Så der er flere ting, vi skal gøre.
Ja, det virker som en rimelig lang liste af ting, men læse papers, skim 2-3 papers, reimplementere. Jeg har ikke kigget dybere, men
Skal vi lige finde ud af, hvordan det sker?
ja, altså jeg tænker, det vigtigste er næsten at finde ud af, hvornår man skal mødes. Altså så længe det ikke er, så er det fint for mig. Men jeg tænker at foreslå tirsdag, bare fordi at altså jeg tror, det bliver presset noget med det der.
Nej, det gør vi ikke. Men skriver det bare ind i Slack.
Ja.
Så skal vi bare finde ud af, hvad vi gør.
Ja, men jeg tænker, at vi bare sidder og spiller. Så giver man update, når man kommer tilbage.
Ja, det var det. Hej.
And I depends. It's here that I can account as you can squeeze this. And also, is this also something that you can squeeze because you don't have the lines again. You don't see so many different. So then, this is three different type of presentations, experimentation. So presentations. This you could do probably. Okay, and then the other thought is.
Yeah, I want to show a little bit of time for figuring out how to do this. So, it's great for a while. As this, I see 50 value, so 2, which is 5, and 13, and then the conflict is and sort of this indicate how much of the drug do you use to respond to this. You can do this for afterwards, which is more. Yeah. So yeah, you get closer to this now. It's just it's a massive hierarchy.
The work with the techniques. We have made experiments with data sets for this. I think 100 patients and then more than 10,000 covariates, and then using specific sparse planning. Priors works fine. Now I try to more like figure out the overall structure.
So this would be sort of my prior drums. This is the response. The response now. And that is now because
So this was
the patient's
patient feature.
Yeah.
Patient feature. Patient features. One file. Five different are I would be able to patients. Paintings. I mean, what no, there's some interaction that specific medicine. Interaction terms.
We didn't put your inspection check. So that's why this is the case.
This is kind of I can think that okay, this is in a way what's in, but then we need to also how much structure we can impose for this. Because in the
Like here, it's like
we have in a way that we have not of it would be now actually a vector because this is also this would be the main effects. And then this would be the interaction curve. But then you would assume that all these are scores because we can have resources. Which is so in a way that these are the